In the next part of 5.2, we're going to be looking at derivatives as a way of seeing when a function is increasing or decreasing. So in a lot of ways, this is similar to things we've done before. And then also finding what's called the antiderivative. Basically, we're going to start working backwards with derivatives. So first of all, when we think about increasing or decreasing function, what we mean by increasing is that as we move from left to right, that everything on the right side is a little bit higher than what was on the left side, or for decreasing, that every point is a little bit lower than what's before it. And so what we know about that is if we look at the derivative, if the derivative is greater than 0, then that means we are increasing. If the derivative is less than 0 or negative, then we're decreasing on that interval. If we're going to determine where graphs rise or fall, then we want to look mostly at the derivative. If our function is y equals x squared, that means that our derivative of this would be 2x. So when we want to find where it's positive and negative, we'll first set this equal to 0, and notice that that's at x equals 0. We can look at a table like this then where we know the only possible change that we have is at 0. Really what we're looking for are critical points here. Remember, our critical points are where we get a 0 or does not exist. In this case, our derivative is equal to 0. That's the only possible changing point. Now, if I look at anything less than 0 and I plug that into my derivative, we'll notice that we always get a negative value. If I plug in a positive value, anything greater than 0, I'm always going to get a positive value. So we're looking at intervals here. X is greater than 0, x is less than 0, and we see that we are decreasing on this side, increasing on this side. And so we'll interpret that as we've got it here. We're decreasing from negative infinity to 0 and increasing from 0 to infinity. Now notice another thing. They've put an a closed parentheses. They've put a closed bracket here, telling us that this interval would be x less than or equal to 0, that it is decreasing. And we're including the 0 in both, and that's actually not a problem, because if we look back at our definition of decreasing, it's saying that as we move from left to right, we're always going down, and anything as we move a little bit to the right is a little bit lower than the point before it. Since this 0 slope is only at an instant, then everything before this was a little bit higher than that. And so we are decreasing everywhere on that interval. This is just the lowest point. And everywhere on the other side, if I start there at that 0, every point is going a little bit up from that. And so I am increasing on that. So we can use a closed bracket when we're talking about increasing and decreasing, which might include two different points. So where is this function increasing and where is it decreasing? Okay, so first we're going to look at the derivative of this, and so we find that that derivative is 6x squared minus 12. And we set that equal to 0, as they've done here. In this particular problem, they've chosen to work with inequalities, but it might be a better idea just to go ahead and set it equal to 0, where we find that the points that we get are the square root of negative square root of 2 and the square root of 2. Those are giving us our zeros. So what we want to check for increasing or decreasing are the intervals between them. If I plug in a 0 to this function here, notice that's always going to give me a negative value. If I plug in anything on either greater than the square root of 2 or less than the negative square root of 2, again plugging them into this function here, then I'm always going to get a positive. This is telling me I'm increasing, I'm decreasing, and I'm increasing on these intervals. Now since it's asking where it's increasing and decreasing, then we can give our answers like this. Notice this time they did not use the or equal to for those values. Okay, where is the function x cubed minus 4x increasing, where is it decreasing? So we're going to start again by taking the derivative, and then we're going to set that derivative equal to 0 to find our critical points. And notice we're going to end up with plus or minus the square root of 4 over 3, whatever that happens to be. Now we might need our calculator to find exactly what those values are, but this is enough for what we're doing. So we know these are our zeros. We'll check between there by plugging into this right here. So maybe I could plug in 0, I'll see I can get a negative. I could put anything larger than that, always going to get a positive, always going to get a positive. And so we can see that I'm increasing prior to this. So increasing from negative infinity to the negative square root of 4/3, and from square root of 4 over 3 to infinity. And I'm decreasing from negative 4 over 3 to square root of 4 over 3. And this next part is looking at what we know, we're kind of working backwards from if we have the derivative, what do we know about the original function? So if we're only given the derivative and we know that it's equal to 0, then we know that our original function must be a constant. Now we don't know what that constant is, but it might be something like f of x equal to 2 or 3 or -5 or something like that. We would also know then that if we have two derivatives that are equal to each other, then we know that they only differ by a constant. Now what this is really telling us, if we take a derivative, say, of something like x squared plus 5 and x squared minus 3, we would end up with both of them getting a derivative of 2x. So the constant always disappears, so if we're working backwards from that, if we know the derivative, then it's going to fit into a certain family that only differs by a constant c. So if we're looking at something like this, we know the derivative is sine of x, and it passes through this point right here. So I know f prime of x is equal to the sine of x. So what I'm thinking about is, okay, well, what function gives me a derivative of sine? If you remember, that would be a cosine of x gives us a derivative of negative sine. So if I have a negative cosine, that would give me a derivative of positive sine. The only thing is I don't know, it might have had a constant on there, so a plus c, that would have disappeared when I took the derivative. Now if this is passing through the point 0, 2, that would mean that my y is equal to 2 when my x is equal to 0. That would give me a negative, that would give me a -1 plus c, and solving that would give me a constant of 3. So going back to my original function here, where I had plus c, I would now plug in this 3, and I know that my original function, f of x equals negative cosine of x plus 3, I would know a couple things about this. First of all, it passes through the point 0, 2, and also it has a derivative of the sine of x. This is called an antiderivative. What we've just done is we've worked backwards from this, and so this process is called antidifferentiation. We're given a derivative and we want to find what function would have that derivative. When we're looking at powers, we can think about the antiderivative like this. Now first, if we're taking a derivative, we want to think about, we take our exponent and we move that in front, multiply it by x, and then subtract 1. So if I'm working backwards, I'm taking an antiderivative, going to f of x. I'm going to do the opposite. So here we are subtracting 1 from my exponent, so it would have to be n plus 1. Now before, I was multiplying by whatever my the exponent of the original function was. So to do the opposite of that, I'm actually going to divide by the exponent of the original function. So whatever we get after we add 1, that's what we divide by here. And that's how we'll take an antiderivative when we have a power function. Another way that we can use this is if we know about acceleration. So this is our acceleration constant for a body falling from rest. So if we're starting from a height of 0 meters, so that's an initial position, and the other thing we'll notice is that it falls from rest. So this is telling us a couple things. Our initial velocity is equal to 0, and our initial position is also equal to 0. Now, if my acceleration then at any time is equal to 9.8 meters per second, then that would mean that my velocity would be an antiderivative of that. So what function would give me a derivative of that? That would be 9.8 t plus some constant. Now we need to solve it and find what that constant is, and we have a little bit of information for here. We know that our velocity at time 0, or 9.8 times 0 plus whatever our constant is, has to be equal to 0. And so our constant at this point is 0. That would mean that our velocity at any time t is really just 9.8 t. Now if I want to find my position, I take an antiderivative of that. Remember that t would become t squared, which would mean that I need to take this and actually divide that by 2. Okay, notice if I take the derivative of this, that 2 times 4.9 would give me 9.8. Now this would also have to be plus a constant, and again we're starting from this position here. We're starting at 0 meters. So again, I would solve this at s equals 0. Basically that's going to tell me that my constant is going to be 0, and so my position function is just going to be 4.9 t squared. Now those two are going to solve for part A here. Now we're going to do this again for part B. In part B, they're telling us some different initial information. We no longer have an initial velocity of 0. We now have an initial velocity, so v at time 0 is equal to 1. So we're starting this by throwing it downward. We have an initial velocity. We still start with the same acceleration, which means we're going to have the same velocity to start out, except here we need to solve for that constant using this information here. Our velocity at time 0 is 1, and so if we plug in that 0 there, we find that our constant in this case is equal to 1. So our velocity function here is 9.8t plus 1. Working from there, we want to find the position function. Again, we would be taking an antiderivative. Just like before, this is going to give me t squared, which is going to give me 4.9 t squared. So again, if I think about this backwards now, if I go 2 times 4.9, it gives me 9.8. The antiderivative of 1 would be t, because if I take the derivative of t, I get 1. And then I always have to consider that there'd be another constant on there. In this case, my initial position is still 0, so my constant is still going to be 0, leaving this as my position function.